What's up? I'm doing a Physics 1 Lab 2 for projectile motion today. Here's our table of contents. It's going to have the introduction, then our fundamental principles, the experimental design, the tracker video model, the computational models for drag and no drag, the graphical comparison, and then the what if. So the purpose was to compare experimental projectile motion with computational models, drag and no drag, to understand how projectile motion works. We're able to see the effects of forces on the position of a projectile over time, like air resistance and gravity. The object was a ball of paper, which experiences drag while moving through the air. Air resistance is not negligible, and there are two separate computational models, one with drag and one without. Fundamental principles utilize Newton's second law, that the net interaction between systems and their surroundings to observe motion changes the momentum of the system. So we're going to be using the velocity update formula, the position update formula, and the force of gravity and drag. It's important to note that if no drag is present, F net equals mg, negative mg. Newton's second law for velocity update, you can see we just get into the change in position and change in force. When force equals 0, then velocity is going to be constant. So for our x position, this is how it's going to look. There's not really much stopping the x direction momentum unless drag's acting on it. The next thing we have is our position update formula. We just use that to calculate the change in position over change in time. So not too much going on there. The next thing is the force of gravity and drag. So obviously force of gravity just equals mg in the negative j hat direction, and drag is b times the magnitude of velocity squared in the j hat direction. B is like the surface area. It's like the cross sectional area of the object thrown. Basically, it's the drag coefficient. If there's no drag, then F net equals F gravity, as said before. For experimental design, a paper ball is thrown in the air in the XY plane. The surroundings include force applied, gravity, and friction. Observational data gathered using the tracker app, and the computational gathered is a Ghost app. And then both trials are going to start at 0, 1 meters, and it's going to go in the negative x direction. So here our procedure was just to make the paper ball and throw it. As you can see in the video here, the tracker tracks its position as it goes across, starting at the X origin. We have our graphs being produced here and our position with a time step of 0.033 seconds. The tracking was done by hand, and sometimes it was a little bit hard to see, so that can be a source for some error. So it's good to keep that in mind when comparing graphs. So for our tracker data, the paper weighed 6 grams. The motion was captured at 30 FPS. The initial position tractor was about 0.1, and same thing with GlowScript. Here are the results below of the computational model. So as you can see in the y direction, we have this nice parabolic curve, and in the x direction, because this is over time, by the way, so this is the x direction, and we can see it's not perfectly linear, so there obviously is a force acting on it, and that would be drag. So here's our GlowScript computational model. We have this right here, which is our just F gravity and F drag updates. Our drag coefficient is right here. So when it equals 0, obviously, as you can see in this graph, it's going to be a nice, perfect parabolic shape. When you make the drag not 0, it's going to change and be something a little different. As you can see, the delta time changes right here. Gravity equals 9.8, and all the regular stuff done here. For the analysis, you can see the tracker data is green, computational is orange, and computational with drag is blue and brown. So you can see that the green, blue, and brown sort of kind of go in the same direction, where the computational is a little bit different. And this is because of the force of drag. It slows it down and makes it go in a different direction. So it's pretty cool to see. This was with an estimated b-value of like 0.001. So it's not perfect, but it's a good approximation. Here's drag plus gravity. You can see the x position x change is pretty nice, and the position y change is a little bit squished as compared to no drag. It's not a perfect parabola. See, it's squished here compared to the no drag. Anyways, to the what ifs. So what does it mean? Terminal velocity happens when a freely falling object experiences zero net force. So examine the velocity time graphs. Do any of your models predict terminal velocity? The answer would be yes for the no drag model, because the velocity, the net force is 0, so it's moving at a constant velocity. However, with the drag, that is not terminal velocity, because we're assuming that drag is canceled out. So if an object was thrown straight up with the same initial speed, would the time this object takes to reach the ground be the same or longer? It would be the exact same. Delta x doesn't change the time it takes to hit the ground. It's the same thing with a bullet versus like a basketball. If they're going to hit the floor at the same time, if their initial y position was the same, it doesn't matter. Gravity affects affects it all. Anyways, thanks for watching.